There's yet another anomaly in particle physics. You've probably seen the headlines. Something with the mass of one of those particles called a W-boson. And supersymmetry is once again the alleged explanation. How seriously should you take this? And why are particle physicists constantly talking about supersymmetry? Hasn't that been ruled out? That's what we'll talk about today. Last time I talked about an anomaly in particle physics was a few months ago, and would you know, 2 weeks later it disappeared. Yes, it disappeared. If you remember, there was something weird going on with the neutrino oscillations in an experiment called LSND. Then a follow-up experiment called Mini-Boon confirmed this, and then they improved the accuracy of the follow-up experiment, and the anomaly was gone. Poof, end of story. No more neutrino anomaly. You'd think this would have taught me to not get excited about anomalies, but you know me better. Now, there's another experimental group that claims they have found an anomaly, and of course we have to talk about this. This one actually isn't a new experiment. It's a new analysis of data from an experiment that was discontinued more than 10 years ago, a particle collider called the Tevatron at Fermilab in the United States. It reached collision energies of about a tera-electron volt, TeV for short, hence the name. The data were collected from 2002 to 2011 by the collaboration of the CDF experiment. During that time, they measured about 4 million events that contained a particle called the W-boson. The W-boson is one of the particles in the Standard Model. It's one of those that mediate the weak nuclear force. So it's similar to the photon, but it has a mass and it's extremely short-lived. It really only shows up in particle colliders. The value of the mass of the W-boson is related to other parameters in the Standard Model, which have also been measured. So it isn't an independent parameter, it has to fit to the others. The mass of the W-boson has been measured a few times previously. You can see a summary of those measurements in this figure. On the horizontal axis, you have the mass of the W-boson. The gray line is the expectation if the Standard Model is correct. The red dots with the error bars are the results from different experiments. The one at the bottom is the result from the new analysis. One thing that pops into your eye right away is that the mean value of the new measurement isn't so different from earlier data analyses. The striking thing about this new analysis is the small error bar. That the error bar is so small is the reason why this result has such a high statistical significance. They quote a disagreement with the Standard Model at 6.9 sigma. That's well above the discovery threshold in particle physics, which is often somewhat arbitrarily put at 5 sigma. What did they do to get the error bar so small? Well, for one thing, they have a lot of data, but they also did a lot of calibration cross-checks with other measurements, which basically means they know very precisely how to extract the physical parameters from the raw data, or at least they think they do. Is this reasonable? Yes. Is it correct? I don't know. It could be, but in all honesty, I'm very skeptical that this result will hold up. More likely they have underestimated the error and their result is actually compatible with the other measurements. But if it does hold up, what does it mean? It would mean that the Standard Model is wrong because there'd be a measurement that doesn't fit together with the predictions of the theory. Then what? Well, then we'd have to improve the Standard Model. Theoretical particle physicists have made many suggestions for how to do that. The most popular one has for a long time been supersymmetry. It's also one of the possible explanations for the new anomaly that the authors of the paper discuss. What is supersymmetry? Supersymmetry isn't a theory, it's a property of a class of models. And that class of models is very large. These models have all in common that they introduce a new partner particle for each particle in the Standard Model. And then there are usually some more new particles. So in a nutshell, it's a lot more particles. What the predictions of a supersymmetric model are depends strongly on the masses of those new particles and how they decay and interact. In practice, this means whatever anomaly you measure, you can probably find some supersymmetric model that will explain it. I'm scare quoting explain because if you can explain everything, you really explain nothing. This is why supersymmetry is mentioned in one breath with every anomaly that you hear of, because you can use it to explain pretty much everything if you only try hard enough. For example, you may remember the 4.2 sigma deviation from the standard model in the magnetic moment of the muon. Could it be supersymmetry? Sure. Or what's with this B-meson anomaly that lingers around at 3 sigma and makes headlines once or twice a year? Could that be supersymmetry? Sure. Do we in any of these cases actually know that it has to be supersymmetry? No. There are many other models you could fumble together that would also fit the bill. In fact, the new CDF paper about the mass of the W-boson also mentions a few other possible explanations. Additional scalar fields, a second Higgs, dark photons, composite Higgs, and so on. There's literally thousands of these models, none of which has any evidence going in its favor. And immediately after the new results appeared, particle physicists have begun cooking up new explanations. Here are just a few examples of those. By the time this video appears, there'll probably be a few dozen more. But wait, you may wonder now, hasn't the Large Hadron Collider ruled out supersymmetry? Good point. Before the Large Hadron Collider turned on, particle physicists claimed that it would either confirm or rule out supersymmetry. Supersymmetry was allegedly an easy-to-find signal. If supersymmetric particles existed, they should have shown up pretty much immediately in the first collisions. That didn't happen. What did particle physicists do? Oh, suddenly they claimed that of course this didn't rule out supersymmetry, it had just ruled out certain supersymmetric models. So which version is correct? Did or didn't the LHC rule out supersymmetry? The answer is that the LHC indeed did not rule out supersymmetry. It never could. As I said, supersymmetry isn't a theory. It's a huge class of models that can be made to fit anything. Those physicists who said otherwise were either incompetent or lying or both. The rest knew it but kept their mouths shut, and now they hope you'll forget about this and give them money for a bigger collider. As you can probably tell, I'm very not amused that the particle physics community never came clear on that. They never admitted to having made false statements accidentally or deliberately, and they never gave us any reason to think it wouldn't happen again. I quite simply don't trust them. Didn't supersymmetry have something to do with string theory? Yes, indeed. So what does this all mean for string theory? The brief answer is nothing whatsoever. String theory requires supersymmetry, but the opposite is not true. Supersymmetry doesn't necessarily require string theory. So even in the unlikely event that we would find evidence for supersymmetry, this wouldn't tell us whether string theory is correct. It would certainly boost confidence in string theory, but ultimately wouldn't help much because string theorists never manage to get the standard model out of their theory, despite the occasional claim to the contrary. I'm afraid all of this sounds rather negative. Well, there's a reason I left particle physics. Particle physics has degenerated into a paper production enterprise that's of virtually no relevance for societal progress or for progress in any other discipline of science. The only reason we still hear so much about it is that a lot of funding goes into it, and so a lot of people still work on it. Most of them don't like me. But the disciplines where the foundations of physics currently make progress are cosmology and astrophysics and everything quantum. Quantum information, quantum computing, quantum metrology, and so on, which is why that's what I mostly talk about these days. The LHC has just been upgraded and started operating again a few days ago. In the coming years, they'll collect a lot more data than they have so far, and this could lead to new discoveries. But when the headlines come in, keep in mind that the more data you collect, the more anomalies you'll see. So it's almost guaranteed they'll see a lot of bumps at low significance that could break the standard model, but then go away. It's possible, of course, that one of those is the real thing, but to borrow a German idiom, don't eat the headlines as hot as they are cooked. As you see, it all comes down to statistics once again. If you think that statistics sounds rather dry and dull, maybe you just haven't seen a good introduction to it. An introduction to statistics that I can recommend comes from Brilliant, who have been sponsoring this video. Brilliant is an amazing tool for learning that offers courses on a large variety of topics in science and mathematics. All their courses challenge you with questions, so you can check your understanding along the way. They have neat interactive visualizations that really give you a feeling for what is going on with the math, and you can learn at your own pace. To learn more about statistics or to freshen up your knowledge, I'd recommend, for example, you check out their courses on probability fundamentals, statistics, and knowledge and uncertainty. To support this channel and learn more about Brilliant, go to brilliant.org/Sabine and sign up for free. The first 200 subscribers using this link will get 20% off the annual premium subscription. Thanks for watching. See you next week.